Well, thanks everyone for being here, and thanks to the organizers for the invitation. And also, before I start, I'd like to thank all my co-authors in this work. So I'm going to be presenting mostly PhD work that I did at Imperial College. And no, it wasn't in Death Valley, it was in Southern Italy. But I also did a bit of work in Death Valley, and it's way more photogenic than Southern Italy, so hence the photo. And I'm going to be focusing on how erosion and sediment export evolve as normal faults do. So I'm going to center the talk in addressing one question, which is how do the magnitudes and the grain sizes of sediment produced and exported from footwall catchments vary during normal fault evolution, and what processes control this? So this question is important to work towards developing functional relationships between uplift, sediment fluxes, and basin stratigraphy during normal fault evolution. Also because it's been shown that the unloading and loading caused by erosion and sedimentation can influence rift evolution, and to understand landscape response to normal faulting. So it touches on several important aspects of normal fault evolution. So just to make sure we are all in the same page, I'd like to give an overview of what are the expected patterns of landscape's erosional response and sediment export during normal fault evolution. So what I'm showing you here is a conceptual cartoon of a normal fault from its tip, where fault flow rates are lower, to its center, where fault flow rates are higher. The rivers that are crossing this fault and draining its footwall catchment are going to try to keep pace with the base level lowering rates that are imposed by the footwall uplift. And in doing so, they are going to incise. And this incision is going to propagate upstream in the form of an upstream migrating nick point, which is this stuff here. These were identified by breaks and slopes in the river long profiles. So as incision propagates upstream, the valid sites are going to steepen, often beyond their equilibrium angles, and landsliding is going to start becoming the dominant erosional mechanism. Oh, sorry, yeah. And this pattern of landscape response can apply to catchments along a fault strike, so as I'm showing here, but we can also think about it as applying to the temporal evolution of a catchment after fault flow rates increase, either following the onset of normal faulting or following a flow rate increment after linkage. So this is useful because it enables us to study the spatial patterns and do some space for time substitutions to infer things about the evolution of erosion and sediment export. So based on all this theory, we can hypothesize that catchment erosion and sediment export are expected to be a function of the fault slip rate and also the degree of transient adjustment to that slip rate. And in this context, the degree of transience can be represented by the extent of incision. So either how far upstream the nick point is, or how much incision depth there is, or how much landslide activity there is. So we selected Southern Italy to test this hypothesis. Here I'm showing you a Google Earth image of Calabria looking towards the southwest. So this is here, the tip of the boot. And here in the background, you can see Sicily and Mount Etna. So I hope you may have already seen that the landscape here is dominated by normal faults that are the result of back-arc extension related to the Tyrrhenian subduction zone. But what makes these normal faults an ideal setting to test this hypothesis is this flat uplifted surface that is a relatively continuous marine terrace level of a terrace that formed just before normal faulting started. So this is very useful for us because it represents, one, a marker of fault throw that allows us to derive a relatively continuous profile of fault throw rate along the fault, and also because it represents a pristine surface that is not adjusted to tectonics, which we can use as a reference to quantify how adjusted other parts of the catchments are. So to clarify what I mean by this reference surface that still has not responded to tectonics, here I'm showing a more zoomed in image of the same areas I showed you earlier, and here a field photo. And I hope you can notice that these catchments are divided by two sectors. Maybe let me go back to make this clearer. So we have a lower sector that is in size, has steep slopes and has landslides. Landslides are these polygons here, which is adjusted or adjusting to tectonics. And we have an upper sector that is unincised and has slow slopes, no landslides, and still has not responded to tectonics. And the boundary between these two sectors is going to be marked by these breaking slopes in the long profiles, by this nick point. So I hope you can see that this is a great place to test this. So I use these and other markers to build high resolution fault throw rate profiles, such as the one I'm showing you here in the bottom. So these I'm showing in the y-axis, the footwall component of the fault throw rate, which is the one that the rivers and the catchments are sensitive to, and the distance along the fault strike. And this is for these 3 faults here. So this data and also some data quantifying the landscape response, and from that reconstructing the fault growth and linkage histories is published in these 2 papers. But for the rest of the talk, the only things you need to keep in mind is that we do have high resolution fault throw rate profiles for all these faults, that all these faults experience an acceleration in fault throw rate 1 million years ago, either due to the onset of normal faulting in Calabria or to a fault linkage event for the southern Apennines. And since then, the footwall throw rates have been up to 0.4 to 0.8 millimeters a year. So I selected 15 of these catchments to do cosmogenic nuclide analysis to estimate catchment average erosion rates. So I'll explain a bit more of this technique in the next slide. So 12 are footwall catchments and 3 are these upper subcatchments above the nick points. So what I'm showing you here is the slope maps of our sample catchment. So you can see that green is lower slopes, and you can see that these catchments have different degrees of preservation of these flat uplifted surfaces. You can also see that they have different degrees of landslide activity. So landslides have these brown polygons, and these numbers represent the landslide aerial densities. So landslides cover between 1 to 30% of the total catchment areas. So we expect them to have a considerable impact on the sediment export from this catchment. And these are just the river-long profiles draining this catchment. This landslide inventory is actually part of a regional landslide inventory that we also publish here. And we also have a field-based area volume scaling relationship. So we can actually also quantify the landslide volumes that are in each of these catchments. So just a brief introduction to cosmogenic nuclides in case you haven't heard from them. So cosmogenic nuclides are nuclides that form in the atmosphere and in the top meters of the bedrock due to the interaction of atoms with the incoming cosmic rays. So they are nuclides such as carbon-14 or beryllium-10 or helium-3. One of the best established applications of cosmogenic nuclides is to estimate catchment average erosion rates. And that is done by taking a sample of the fluvial sediment at the outlet of the catchment that we assume contains a representative mix of grains from all across the catchment. And after a lot of lab work and AMS measurements, we obtain a catchment average erosion rate. And that is because here, this is the concentration of cosmogenic nuclides, and this is inversely related to the surface erosion rates here. So measuring the beryllium-10 concentrations, I obtained catchment average erosion rates of between 0.08 to 0.64 millimeters a year. So here I'm showing you the same catchments as I showed you earlier, but this time plotted in their position along strike where they are in the different faults. And this erosion is representative, so represents integrated erosion over 1 to 7,000 years. I can combine my data also with some published data by Sarah et al. Here and by Olivetti et al. And one thing I noticed is that all the samples that are from these unincised upper subcatchments above the nick points are eroding at very consistent rates of about 0.1 millimeters a year. So I consider this the background erosion rate that is operating in the area in absence of any tectonic forcing. So if I plot the catchment average beryllium-10 erosion rates here on the y-axis against the footwall component of the fault throw rate in the x-axis, so this is derived from these continuous profiles that I showed you earlier, we can see that there is a good correlation. And if we set up the intercept at this background erosion rate of 0.1 millimeters a year, we can see that on average, erosion is removing about half of the rocks that are being uplifted by the fault. I should also say that these large uncertainties here are mostly mostly arise from the uncertainties in the dates of the marine terraces. So they are lastly systematic. And also some of these scatters that we see here, we know has to do with lithology. So for example, we do know that granites in this area are about twice as weak as the gneisses. And for similar fault throw rate range, they seem to be eroding about twice as much. So we can confirm the first part of this hypothesis. But as I said earlier, we expect this to be mediated by incision and landsliding, which should also scale with the fault uplift rate. And indeed, that's what we do find. So here I'm showing the catchment maximum incision in the y-axis. This is derived from the DMs against the same footwall fault throw rate. And we can see that fluvial incision is controlled by the fault throw rate. And also because we know when incision started, we can calculate incision rates. And we see that incision is operating at very similar rates of between 0.1 to 0.6 millimeters a year as the erosion rate. So how does this landscape response influence sediment production? So it does so because as rivers in size and adjust to the uplift rates, hill slopes stiffen and starts to produce landslides. So here I'm showing to the left on the y-axis the same erosion rate I showed you earlier, this time against the maximum incision. And here in this other graph, I'm showing the total volume of landslides in each catchment against the maximum incision depth. So we can see that both increase in a very similar manner, and that as incision progresses, erosion and sediment fluxes increase because landslides get bigger and more frequent. This is important because we know that landslides deliver coarser grain size distributions than other sediment production processes. And we know that grain size is important in reef settings because it has a big control on stratigraphy and also in the reservoir potential of the reefs. So we actually quantified how much coarser material they deliver by doing point count on the material that was in landslide deposits and also the material that was being sourced from physical weathering in outcrops. So what I'm showing you here is D84. That's the 84th percentile of these grain size distributions. So sorry, it's a box plot of the 84 values for different lithologies and for different processes for each of the lithologies. So the empty boxes are landslides and the filled ones are physical weathering products. So what we can see is that landslides consistently deliver coarser grain size distributions. So therefore, we can hypothesize that catchments that are affected by greater flow rates or greater transient responses, which have greater incision and greater landsliding, should also export coarser grain size distributions. So to test this, we also measured the grain size distributions in the fluvial sediment in the same locations where we took our beryllium-10 samples. So here again, I'm showing the 84th percentile of the distribution against the maximum incision in the catchment. And we can see that over a 600 meters increase in incision, the grain size basically doubles. And we also find that the same the 84th percentile distribution correlates with our beryllium-10 estimated sediment fluxes from the catchment. So we can confirm this hypothesis. And this is due to the fact that large sediment fluxes in this area at least can only be achieved through more intense landsliding, which we also know delivers coarser grain sizes. So as the catchments are adjusting to an increase in fall slip rate, in this case due to spatial differences, but we also think that this could maybe be extrapolated to the time evolution, they experience a coupled increase in the sediment fluxes and the grain sizes that they export. So just to wrap up, I'll just leave you here with the main questions we've addressed, the two hypotheses that we have tested with our field data, and we've shown that basically it's the landscape response that mediates the tectonic control of sediment production. Thank you.
Thank you, Duna. Do we have any questions?
How can I see the question?
So far, there's no question. Maybe people are typing.
Yeah.
You don't have to type the question. You can just type a question and then you get the word.
Can I ask a question?
Yeah, go ahead.
Hello, hi Duna.
Hey.
Really good talk. Yeah, really nice to hear it. I was just thinking about your talk and Bailey's talk, and Bailey was talking about this, possible fault tip retreat and what happens when faults die and maybe they kind of contract. Do you think that's something that might be possible to be constrained with more kind of surface geomorphological data, or do you think that wouldn't really be possible?
I think definitely in stratigraphy, potentially. We could also see by the grain size, I mean, not only by the accumulation rate. If it was in the landscape, I think we can definitely see the decay stage in incision and landsliding and the relaxation of hill slopes in faults. I'm not aware that that has been shown in normal faults, but I know in the Mendocino triple junction, which is in transversion, it's been recently shown by Fiona Club and colleagues. So yeah, potentially we could see that also in the landscape.
Cool. Okay, thank you, Duna.
Thanks.
I would also have a question related to what Becky just asked. Are there any normal faults in Italy that are not active anymore? Any dead normal faults? And maybe the response of how they died is still there in the landscape?
I think there are actually, but I'm not super familiar with them because when I was doing the PhD, I was just trying to find the active ones. But I think there certainly are. So it will be super interesting, yeah, to look at their geomorphic patterns and stratigraphy there.
Okay, thank you.
Thanks.
There's something going on in the chat, but I'm not quite sure which of them is a question and which of them is the answer.
Okay.
I think there's a question by LANSCAPE'S to Duna.
Yeah, sorry, I cannot see. I'm trying to open the chat and I can't, and every time I just keep
That's
opening
right.
my presentation.
Can you ask the question yourself?
Yeah, I could hear it, but I cannot see it.
Maybe I read it. Is this applicable to ancient normal faults? And can we start with something like grain size and back out to rates of incision or fault motion?
Definitely, that would be the goal. That would be super cool. I think we do need more field data to calibrate models. And of course, one thing I haven't touched on is that the transport capacity of these catchments is also very important. So as they incise, they also are able to transport more of this coarse material that is being delivered. But it's also something to take into account. But yeah, that would be the goal, I think, to be able to just take grain size patterns and reconstruct what was the transient response of what was the fault doing.
Okay. Then we have one last question before we move on. That's from Aksai. Do you want to ask it yourself?
Yeah, sorry, I just saw it now. I finally could open the chat. Did you only observe and map landslide deposits near fault zones in your study area, or also some synkinematic fluvial sedimentary structures, sedimentary wedges implications in relation to gradual faulting? So if the question is if I mapped the hanging wall fluvial sediment, no, I didn't. And I think in some areas, there's quite a lot of incision, and I think definitely you can see the grain size patterns quite well. In some other areas, they are very heavily agricultured, and there's not so much incision. So unless you trench, it would be hard to actually do a good map of the grain size patterns in the basin.
Okay, thanks again, Duna. And then we move on to Zoe.